Good morning, everyone. I'm Rahul Chowdhury, and welcome to our fascinating journey into CPU architecture. Today, we're going to dive deep into understanding the brain of your computer, the central processing unit. Think about it: every time you click a button, type a letter, or run a program, your CPU is working behind the scenes, processing billions of instructions every single second. It truly is the brain that makes everything possible. Just imagine billions of instructions per second. That's an incredible feat of engineering. But how does it actually work? That's what we're here to discover together. And here's the exciting part. Once you understand how CPUs work internally, you'll be able to write more efficient software, optimize performance, and truly appreciate the elegance of computer architecture. Throughout our course, we'll explore the key components, understand instruction cycles, and learn practical performance optimization techniques that you can apply in your own programming projects. To help us visualize this complex system, I want you to think of the CPU as a highly efficient factory assembly line. Just like a factory takes raw materials and transforms them into finished products, the CPU takes instructions and data, processes them through various stages, and produces results. This analogy will guide us throughout our exploration. By the end of today's session, you'll have a solid foundation in CPU architecture that will serve you well in your computer science journey. Let's begin this exciting exploration together. Now that we've covered the fundamentals, let's dive into the heart of our study, the core components that make up a CPU. Think of the CPU as a bustling city, and we're about to explore its most important districts. Here are the 5 essential components that work together as the brain of every computer. Each one has a specific role, just like departments in a well-organized company. First, we have the control unit, or CU. Picture this as the traffic controller at a busy intersection. It directs the flow of instructions, telling other components when to act and what to do. Without the CU, chaos would reign in our CPU city. Next is the arithmetic logic unit, the ALU. This is your CPU's calculator. It performs all mathematical operations like addition, subtraction, and logical comparisons. Every computation you see on screen started here in the ALU. Registers are like the CPU's personal workspace, ultra-fast temporary storage that sits closest to the processing cores. Think of them as the desk drawer right next to where you're working, containing the tools and data you need most frequently. Cache memory acts as a high-speed buffer between the CPU and main memory. Imagine it as an express lane at the grocery store. It holds the items you're most likely to need next, dramatically speeding up access times. Finally, the clock serves as the metronome for all CPU operations. Just like musicians need a beat to stay in sync, every component in the CPU follows the clock's rhythm to coordinate their activities perfectly. Remember, these 5 components don't work in isolation. They collaborate seamlessly as the brain of your computer. In our next section, we'll see how they're organized and connected in the overall CPU architecture. Now let's step back and see the bigger picture, how all these CPU components we just covered work together in a unified architecture. Welcome to our CPU architecture overview. This slide shows us the fundamental organization that ties everything together. First, let's understand the 2 main architecture models. Von Neumann architecture uses a single memory space for both instructions and data, while Harvard architecture keeps them separate. Most modern CPUs actually use a modified Harvard architecture for better performance. The data path is crucial. It's the highway system that controls how information flows between all our CPU components. Think of it as the traffic management system ensuring data gets where it needs to go efficiently. These pathways are implemented through bus systems. The address bus carries memory locations, the data bus carries the actual information, and the control bus manages the coordination signals. Together, they form the CPU's communication network. Memory hierarchy shows us how storage is organized by speed and size. Registers are lightning fast but tiny. Cache is very fast and small. RAM is fast and medium-sized, while storage is slow but massive. This pyramid structure optimizes both speed and cost. Modern CPUs take this further with multiple cores sharing resources like cache and memory controllers. This allows parallel processing while maintaining efficient resource utilization. This architectural overview gives us the foundation to understand how instructions actually move through the CPU. Next, we'll dive deep into the instruction lifecycle, starting with the fetch phase. Perfect. Now let's dive deep into the instruction lifecycle, starting with the fetch phase. This is where it all begins, how the CPU actually gets the next instruction to execute. The fetch phase is the first critical step in instruction execution. Think of it like a librarian systematically retrieving books from specific shelf locations. Step 1, the program counter. Our trusty GPS points to the memory address where the next instruction lives. It's like having the exact shelf number for the book we need. Step 2, the CPU sends this address to memory through the address bus. Picture this as writing down the shelf number and handing it to our librarian. Step 3, memory responds by sending back the instruction through the data bus. Our librarian has found the right book and is now carrying it back to us. Step 4, the retrieved instruction gets loaded into the instruction register. This is like placing the book on our reading desk, ready for us to open and read. Finally, Step 5, the program counter increments to point to the next instruction address. Our GPS updates to the next destination, preparing for the next fetch cycle. This entire fetch process happens billions of times per second in modern CPUs. Now that we've understood how instructions are fetched from memory, let's dive into the next crucial phase, the decode phase. This is where the CPU becomes a detective, analyzing and interpreting what each instruction actually means. Welcome to the instruction lifecycle decode phase. Think of this as the CPU's translation department, where raw binary instructions get converted into actionable plans. First, the control unit springs into action. It carefully analyzes the instruction's opcode. That's the operation code that tells us what to do and identifies the operands, which are the data or addresses the instruction needs to work with. Next comes format decoding. The CPU determines exactly what type of operation needs to be performed and where all the required data is located. Is it an arithmetic operation, a memory access, a jump instruction? This step figures it all out. Then we have resource identification. This is like the CPU checking its toolbox. It identifies which registers will be needed, what ALU functions are required, and whether memory access will be necessary. Everything must be ready before execution begins. Finally, the decode phase generates control signals for the upcoming execution phase and prepares all operands. It's like a conductor preparing the orchestra. Every component gets its cue for the performance that's about to begin. The instruction is now fully understood and ready to be executed. Perfect. Now we arrive at the climactic moment, the execute phase. This is where all that preparation pays off and the CPU actually performs the work. The execute phase is truly the final phase where actual computation happens. Think of it as the moment when our orchestra finally plays the music after all the preparation. First, we have ALU operations. The arithmetic logic unit performs mathematical calculations like addition and subtraction, as well as logical operations like and, or, and not. This is the brain doing the actual thinking. Next, memory access operations handle load and store instructions. When the CPU needs data from memory or wants to save results back to memory, this is where it happens. Register updates are crucial. The CPU stores computation results in registers for quick access. These are like the CPU's scratchpad for immediate use. The CPU also updates status flags during execution. The carry flag indicates arithmetic overflow. The 0 flag shows if a result is 0, and the overflow flag detects when numbers get too large. These flags help the CPU make decisions in future instructions. Finally, results are written back to their destination, either to registers for immediate use or to memory for long-term storage. This completes the instruction execution cycle. So in summary, the execute phase transforms decoded instructions into actual computational work, performing calculations, accessing memory, updating registers, and setting status flags. It's the payoff moment, where all that fetching and decoding finally produces results. Now that we understand how individual instructions flow through the CPU, let's explore a powerful technique that dramatically improves performance: pipelining. Pipelining is one of the most fundamental optimization techniques in modern CPU design. Think of it as the difference between washing dishes one at a time versus having an assembly line. The assembly line analogy is perfect here. Instead of waiting for one instruction to completely finish before starting the next, we can have multiple instructions in different stages simultaneously. One instruction might be fetching while another is decoding, and a third is executing. Let's examine the classic five-stage pipeline that forms the foundation of CPU design. Stage 1, fetch, retrieve the instruction from memory. Stage 2, decode, interpret what the instruction means and prepare the necessary resources. Stage 3, execute, perform the actual computation or operation. Stage 4, memory, access data from memory if needed. And Stage 5, write back, store the results back to registers or memory. The key benefit is remarkable. Ideally, one instruction completes every single clock cycle. This gives us much higher throughput, more instructions processed per second, even though each individual instruction still takes the same amount of time to complete. Modern CPUs take this even further, with pipelines having 10, 15, or even 20+ stages. Deeper pipelines allow for higher clock frequencies, though they also introduce new challenges that we'll explore in our next topic. Now that we've explored the benefits of pipelining, we need to address the challenges that can disrupt this smooth operation. Let's examine the hazards that can occur in pipeline processors. Pipeline hazards are situations that prevent the next instruction from executing in the following clock cycle, essentially breaking our ideal pipeline flow. First, we have data hazards. These occur when an instruction depends on the result of a previous instruction that hasn't completed yet. For example, if one instruction writes to a register and the next instruction needs to read from that same register. Control hazards happen when we encounter branch instructions. Since we don't know which path the program will take until the branch is resolved, the pipeline doesn't know which instruction to fetch next, disrupting the sequential flow. Structural hazards occur when multiple pipeline stages compete for the same hardware resource simultaneously. This creates a resource conflict that must be resolved. Fortunately, we have several solutions to address these hazards. Forwarding allows us to pass results directly between pipeline stages without waiting for the write-back stage. Branch prediction helps us guess the outcome of branches, and pipeline stalls give us time to resolve conflicts when necessary. Modern CPUs take this even further with out-of-order execution, allowing instructions to execute as soon as their dependencies are resolved, rather than in strict sequential order. This significantly minimizes the impact of hazards on performance. Excellent, now that we understand how out-of-order execution helps minimize pipeline hazards, let's explore the broader landscape of parallelism in modern CPUs. Today's processors employ multiple sophisticated techniques to maximize performance by doing more work simultaneously. We're going to examine 5 key forms of parallelism that go far beyond the basic pipelining we've already covered. These techniques work together to squeeze every bit of performance out of modern processors. First, let's look at superscalar execution. This technique allows the CPU to issue multiple instructions per clock cycle, not just one. Think of it like having multiple checkout lanes at a grocery store. Instead of processing one customer at a time, you can handle several simultaneously. Next, we have multi-core processors, essentially multiple independent CPUs on the same chip, each with their own execution units, but sharing memory and cache resources. This is like having multiple complete kitchens in a restaurant, each capable of preparing different dishes simultaneously. Simultaneous multi-threading, or SMT, takes this further by allowing multiple threads to execute on the same core simultaneously. Intel calls their implementation hyperthreading. It's like having one chef who can work on multiple recipes at once, switching between them whenever one needs to wait. Vector processing uses SIMD, single instruction, multiple data operations. This means one instruction can operate on multiple pieces of data simultaneously, like adding corresponding elements of two arrays in a single operation. It's incredibly powerful for mathematical computations and multimedia processing. Finally, speculative execution allows the CPU to predict which instructions will likely be needed next, and start executing them before it's certain they're required. It's like a chess player thinking several moves ahead. If the prediction is correct, you save time. If wrong, you discard the work and continue. The key benefits of all these parallelism techniques are improved throughput, better resource utilization, and enhanced performance for complex workloads. When combined effectively, they can provide dramatic performance improvements over simple sequential execution. Now that we understand how pipelining and parallelism work together, let's examine the key factors that actually determine how fast your CPU performs in real-world scenarios. These performance factors will help us understand what we'll see in our upcoming demonstration. First, we have clock speed. This is probably the most familiar factor to you. Higher frequency means the CPU can execute instructions faster, but it's not the whole story. Think of it like the heartbeat of your processor. Cache hit rates create massive performance differences. When data is found in cache versus having to fetch it from main memory, we're talking about speed differences of 100x or more. This is why cache design is so critical. Pipeline efficiency ties directly to what we just covered. Remember those hazards we discussed? Data hazards, control hazards, and structural hazards all reduce the effective throughput of our pipeline, even with the same clock speed. Memory latency is often the hidden bottleneck. Even the fastest CPU has to wait when data isn't readily available. This is why we have complex memory hierarchies and why cache performance is so important. Finally, branch prediction accuracy can make or break performance. When the CPU guesses wrong about which instruction comes next, it has to flush the pipeline and start over, wasting all those cycles we worked so hard to optimize. Understanding these factors is crucial because they all interact with each other. In our next demonstration, you'll see these principles in action and observe how CPU wait times actually impact real performance. This will make the theoretical concepts we've covered much more tangible. Perfect. Now let's dive into the actual measurements that reveal the harsh reality of CPU performance. This demonstration will show you exactly why understanding memory hierarchy is so crucial. Let's start with CPU cache access, the fastest memory your processor can reach. At just 1 to 4 clock cycles, this is lightning fast. The CPU barely notices this delay. But look what happens when we need data from main memory RAM. Suddenly we're waiting 100 to 300 cycles. That's already a significant wait time for the CPU, which could have executed hundreds of other instructions during this delay. Now here's where it gets dramatic. SSD storage access takes around 25,000 cycles. The CPU is practically idle during this time, waiting patiently for the data to arrive. This is why operating systems do context switching during I/O operations. And traditional hard disks, we're talking about 10 million cycles. In computer time, this is literally forever. The CPU could execute billions of instructions while waiting for a single hard disk read. This brings us to a profound realization about modern computing. CPUs spend most of their time waiting, not computing. This is why techniques like caching, prefetching, and parallel processing are absolutely essential for performance. In the next section, we'll explore how to optimize for CPU efficiency given these constraints. Now that we understand the constraints and performance factors, let's explore how we can optimize our code for CPU efficiency. This is where theory meets practice. First, cache-friendly programming. Remember our discussion about cache memory. By optimizing data locality, keeping related data close together in memory, we can dramatically reduce cache misses and improve performance. Second, pipeline-aware coding. Since we've learned how instruction pipelining works, We can write code that minimizes branches and dependencies, allowing the CPU to maintain smooth pipeline flow without stalls. Third, parallel algorithm design. Modern CPUs have multiple cores, as we discussed earlier. Effective parallel programming leverages all available cores to divide work and process tasks simultaneously. Fourth, memory hierarchy optimization. Understanding the speed differences between registers, cache, and main memory helps us keep frequently accessed data in the fastest possible storage locations. The key insight here is that understanding CPU architecture doesn't just satisfy curiosity. It fundamentally changes how you approach programming problems and makes you a more effective developer.